consider again the mother function y equal to sine theta, the green graph here. If we want to vertically stretch this graph, then we have to multiply this f of sine theta with a factor. In this case, we have a factor of 2. So we multiply each y value because the sine theta here is the y value. The theta is the independent value and sine theta is the dependent value. So we multiply the y value by 2 each time. So we pick a few values, like for instance at a we get 0, multiply by 2 to get 0 again. At b we have -1, if I multiply by 2 I get -2. At c I will get 0 again. At d I multiply by 2 I get I, which is 2. And at e I get 0 again. At f I multiply by 2 again and I get -2 and I make a dot there. At g I stay at 0 because 2 times 0 is 0, and here at 450 degrees I get a maximum value of 1. If I multiply that by 2 I get +2 and I make a dot. Once we've joined the points A and H and C and I and E and J and G and K and etc., when we join it we look at the form, and remember we have to join it in the same manner as the graph, so it may not look like straight lines. It is a curved, it's same curving as the regular sine graph. So we join this and then we want to look at the properties of this graph. First of all, we have to look at the period. So we saw that the period of the regular or the mother graph is 360 degrees, and then we look at the stretch one, which is now 2 times sine theta, and we see that if you look from A through H, through C, through I, up to E, we get exactly the same image as when we do it from E to J to G to K, etc. So the period is exactly the same as before, which is 360 degrees, which we get 180 minus 180 degrees, so that gives us 360 degrees. 360 degrees. So the next thing we need to look at is the amplitude, and we know the formula for the amplitude is the maximum minus the minimum divided by 2, so we have a maximum of 2, we have a minimum of -2, and we divide it by 2, and that will give us 4 divided by 2, which is 2. The roots, if we look at the roots, we actually need to solve algebraically this equation, and we see it will give us exactly the same roots or solutions as if we just solve sine theta equal to 0. So we have exactly the same roots at A, at C, at E, at G, etc. So a general formula for the roots is we can write theta equal to K times 180 degrees, where K is an element of Z. If I make K equal to 0, if K is 0, I will get point C back 0. If I make K equal to 1, I will get 180. If I make K equal to 2, I will get 360 degrees. If I make K minus 1, I will get minus 180 degrees. The extremes, they are Y values. So, and we have our minima at -2 at H and at J, and both of them are -2, so the minima is -2 and the maxima are Y equal to +2. So that happens at I and K. So we can write down a formula for where we get the minima and where do we get the maxima. It is not the minimums and the maximums, it is where we get it. It's the places we will find them, and that we can look at H, go to the horizontal axis, read it off there, we get -90 degrees, and we add 360 times K, where K is an element of Z. And the same for I, will get 90 degrees plus k times 360 degrees k element of z. Because from h to j we get 360 degrees difference. And the same from I to k, there's a 360 degree difference. So this is our minima and our maxima as well as our roots. The next page just gives you a summary of what we've said before, and it's just the type version of what we've written out. And what you should note is that the coefficient of the sine theta here and the amplitude coincide. So it's the same thing. So the rest are just here for you to take note of, and it's better to understand it than to memorize it, but this is the basics or the must-knows that you need to know about vertical stretching. So let's move on to vertical shrinking. So if you look again at the coefficient of G, we see that we now have a half, which is less than 1 and also greater than 0. So it means that each and every y value, we take that and divide it by 2. So if you take 0 divided by 2, I will still get 0. If I take minus 1 divided by 2, I'll get negative a half. 0 divided by 2, 0. 1 divided by 2 gives you half. 0 minus a half, 0. So these are the points that we have to make in order to draw our shrinked sine graph. Now we've joined the points and we can see the red graph there is the graph of G. It has a similar shape as that of the green graph. It is just flatter. It is shrinked vertically. So let us again look at the period and the other properties of this graph. First of all, you'll notice that the period stays exactly the same because from A through H through C, I and up to E we get the same graph or same form as when we go from E, J, G, etc. It doesn't show on the graph, but we can easily deduce it from what we see. So the period stays 360 degrees. If we look at the amplitude, then we see that the maximum is now at a half, and the minimum is at minus a half. So if we add that, we get 1 divided by 2, and that will give me a half. So that's our amplitude, and this is this distance here from the horizontal axis up to the maximum value, or from the horizontal axis to the minimum value when the graph is in standard position. Let us look at the roots. Again, if I want to solve a half sine theta equal to 0 algebraically, it will give us the same solutions as when I solve sine theta equal to 0. So a half sine theta and sine theta has exactly the same roots. So if I look now at the graph, I see the roots will be minus 180, 0, 180 and 360 degrees. So in general, we can write down theta is equal to k times 180 degrees, where k is an element of z, and you can test again by substituting values for k. If k is 0, I will get point C. K is 1, I will get 180, k equal to 360, and so forth. So the extremes in this case are y equal to negative a half and y equal to plus a half. Those are the extremes, and we will find it at H and I and J. So the minima, we can look at the minima, we can write down the horizontal or the independent variable here, which is minus 90. It is at that point. It is not the minimum. It is at the point, so we get minus 90 degrees. Plus, again, from there to the next minimum, we have 360 degrees. So it's plus k times 360 degrees. And the maximum of plus 90 degrees plus k times 360 degrees. Which we can't see it now on the graph, but the next one will be here somewhere. So that part there will be 360 degrees. So, in general, we can summarize what we saw on this graph by looking at the next page. Here is now the summary of vertical shrinking. If I have sine theta versus a half sine theta, then it will shrink the sine graph vertically with a half, factor of a half. And we notice again that the half here and the half there coincide with each other. The amplitude is the A that's in front, but it's the absolute value of the A in front of the sine theta. We will get to the general form of this of a sine function, and then from there onwards we will look at it again. So the rest are now just typed out so that you can use it as a reference, and then you can look here again. The note here is exactly the same as we had on the previous page. You can now go to the exercise where we have a few graphs that test your knowledge about vertical shrinking and stretching to identify the graphs and their properties on that one image.